Assuming a closed system, calculate the amount of energy required to convert 237 grams of solid ice at 0.0 degrees Celsius to hot water at 80.0 degrees Celsius. The molar heat of fusion of ice is 6.01 kilojoules per mole. The molar heat capacity of liquid water is 75.3 joules per mole degrees Celsius. Before we get to the actual numbers here, let's take a moment to think about what's happening conceptually. Generally speaking, as you add heat to a substance, it warms up. In fact, the more substance you have, the more heat you'll need, so it's important to pay attention to amount. As a substance undergoes a phase change, however, it spends some time at constant temperature. Different substances heat up or change phase at different rates, so it's also important to pay attention to the characteristics of the specific substance being heated. Consider now the heating curve for water. If we start with a block of ice well below the freezing point and heat it up until it becomes steam well above the boiling point, you get a chart that looks like this. Notice the two horizontal sections. One, at 0 degrees Celsius, occurs as the ice is melting. The other, at 100 degrees Celsius, occurs as the water boils. While the H2O continues to absorb heat at a constant rate during these plateaus, the energy absorbed contributes to the phase changes occurring, rather than an increase in temperature. Once all of the solid ice is converted into water, additional energy now works to increase the temperature of the substance. The different sections of the heating curve represent slightly different types of thermodynamic processes. When we need to solve a heating problem similar to the one we have before us then, it can be helpful to break it up according to these different processes. For our problem, we have two parts: the phase change from solid ice to liquid water at 0 degrees Celsius, and the heating of liquid water from 0 degrees Celsius to 80 degrees Celsius. Therefore, we need to determine the amount of energy required for each section of the heating curve, and then add them together for the overall solution. In the first part, we know that we have 237 grams of ice, and that the heat of fusion for ice is 6.01 kilojoules per mole. In the second part, we know that the same 237 grams of liquid water is heated from 0 degrees to 80 degrees Celsius, and that the molar heat capacity of water is 75.3 joules per mole degrees Celsius. Sidebar here. Remember that in chemistry we use two different sets of units to represent substance, mass and moles. In any problem where the amount of substance is significant, it's of critical importance that we determine which amount to use in our calculation. When trying to determine whether or not you should use mass or moles, I like to refer to the old adage, units don't lie. Check your units. Make sure that the amount of units for each number are in agreement. For instance, 237 is measured in grams, but 6.01 is kilojoules per mole. Thus, we need to convert one of our units before multiplying these numbers. For part 1, convert mass to moles and then multiply by the heat of fusion. 237 grams of ice represents 13.2 moles of ice times 6.01 kilojoules per 1 mole of ice melted. This requires 79.3 kilojoules to melt all of this ice. Now we have the same amount of H2O, 13.2 moles, that needs to be heated 80 degrees, and it requires 75.3 joules per mole of water for every degree Celsius. For the second section, it takes 79,500 joules of energy, or 79.5 kilojoules. If we add the kilojoules required for each part of this problem, we arrive at our final answer. 158.8 kilojoules of energy are required to convert 237 grams of ice at 0 degrees Celsius to hot water at 80 degrees Celsius.